In this example, we're going to prove that the L2 norm is actually a norm. Okay, well, there's three pieces that we have to prove: positive indefinite, absolute homogeneity, and the triangle inequality. Okay, so for a vector x, and we'll call it x1, x2, xn, the L2 norm of x is the square root of the sum of the xi's squared. Right, so you take each component, you square them, you add them up, you take the square root. And so positive definiteness, we know that the square root of anything is going to be greater than or equal to 0. So the one norm is the square root of the sum of the xi squares, which is greater or equal to 0, because any square root is greater than or equal to 0. And the only time that the square root is equal to 0 is when the thing inside the square root is equal to 0. So the sum of the xi squared is equal to 0 if and only if the sum of the xi's, the sum of the xi squareds, equal to 0. And if you add a bunch of squares together, since every perfect square is greater than or equal to 0, the only way a bunch of perfect squares are equal to 0 is if each xi is square, each xi squared is equal to 0, which means that each xi is equal to 0, which means that our x has to be a vector of zeros. Okay, so the only way that the one norm of x is equal to 0 is if x is a 0 vector and the one norm of x is always greater than or equal to 0. Next, we want to show that the norm of alpha x for any vector x is equal to the absolute value of alpha times the norm of x. And of course, we're doing this with the 2 norm, the Euclidean norm, not the 1 norm. Okay, so this is going to be the sum, or the square root, I should say, of the sum of the absolute value of alpha xi. Oops, not the absolute value. What am I doing here? It's the absolute value, or sorry, the sum of the alpha xi squareds, which is going to be the square root of the sum of alpha squared times xi squared so that's alpha squared times x1 squared plus alpha squared times x2 squared, so on. So this is just really the root of alpha squared times the sum of each of those xi squareds. And of course, this is the absolute value of alpha, if we bring that outside of the square root, times the root of the sum of the xi squareds. And the root of the xi squareds is just the 2 norm of our vector x. So we have absolute homogeneity. And finally, the triangle inequality. The triangle inequality is a little bit different here. we want to show that the absolute value of x plus y, using the 2 norm, is less or equal to the absolute value of x plus the 2 norm of y. Okay. So the first thing that we want to remember is that the norm squared, so these are facts that we know. The 2 norm for any vector, we'll call it A, squared is equal simply to the sum of AI times AI, right? It's the components squared, which is the same thing as A, vector A, dot vector A. So it's the same thing as the dot product, right? So any 2 norms squared is the dot product of what's inside it. Okay, that's important because this gives us then that the norm of A plus B for any vectors A and B squared is going to be A plus B dotted with A plus B and if we look at that dot product, we get A dot A plus B dot B plus 2 A dot B. And that's important because A dot A is norm of A squared. B dot B is norm of B squared. Okay. The other thing that we need to remember is fact 3, the Cauchy-Schwarz inequality states that the absolute value of AB, A dot B, is less than or equal to the norm of A times the norm of B. The absolute value of the dot product is less than or equal to the norm of A times the norm of B. Okay. So using these facts, we can prove this inequality. So the absolute value, the 2 norm of x plus y squared is then going to be equal to the norm of x, norm of y, plus 2x dot y. And of course, 2x dot y by the Cauchy-Schwarz inequality is going to be norm of a squared, 2 norm of a times 2 norm of b. So x is the 2 norms, by the way. Norm of x squared plus norm of y squared plus twice norm of x, norm of y. But this is equal to the norm of x plus the norm of y squared. Just by looking at that, noticing that it's the completion of that square, right? We've just factored it. And because norms are greater than or equal to 0, this is the same as saying that the norm of x plus y is less than or equal, using this weakest inequality piece, the norm of x plus the norm of y. So in fact, the triangle inequality does hold in this case.